this helmet on your head, and you can visit any year you choose. You could even travel into the far future.
Time travel, an age-old concept, involves the journey to the past or future. To establish the foundation, consider Einstein's theory of relativity, which asserts that our perception of the now constantly shifts in sync with time. Our experience of time passing is shaped by our accumulation of memories and knowledge, fostering a continuous flow throughout our timeline. This phenomenon arises from the wiring of human brains, as Einstein noted. Those who adhere to physics understand that the division between past, present, and future is merely a stubbornly persistent illusion. What if our entire comprehension of time is merely a mirage? Can we potentially disrupt the natural progression of the universe to escape this illusion? In this video, we'll delve into these questions and more. When we think of time travel, it typically involves a person journeying forward or backward in time while maintaining their physical form. It would be rather amusing if you were to travel back 20 years and encounter a baby version of yourself. However, imagine stepping out of the time machine as a baby, resembling the very infant you initially intended to visit. In our conventional perception of time's progression, we are, in fact, traversing from the past to the future. Diverse interpretations exist, but when people mention time travel, they generally refer to either advancing to the future rapidly or journeying into the past. Regardless, we're altering the rate of time's progression by an amount denoted as x. In Newtonian mechanics, time appears linear and deterministic. However, since Albert Einstein introduced the theory of relativity, the classical concept of absolute time and space has given way to the notion that time carries subjective significance for each individual. In this framework, time is one dimension within the space-time continuum of special relativity, or it plays a role in the dynamic curvature of space-time in general relativity. Under this perspective, the prospect of moving backward or forward in time might not be as implausible as it seems. In this scenario, it could be as straightforward as ordinary individuals transitioning between different points in space. Numerous hypothetical scenarios for time travel have been proposed over the years, often distinct from the traditional idea of a physical machine with levers and dials, like the one Herbert George Wells envisioned. Notably, Einstein demonstrated that time behaves differently in various situations, indicating that time passes at varying rates for different observers, depending on their relative traveling speed. For instance, consider astronauts aboard the International Space Station, which orbits Earth at a speed of 28,000 kilometers per hour. When you consider the interplay of different factors in this scenario, you arrive at the net effect of time dilation. This effect is due to the astronaut's velocity compared to an observer on the Earth's surface. Astronauts aboard the spaceship experience a noticeable amount of time dilation each day, particularly for a typical crew member who spends 6 months on the International Space Station. There may be a scientific basis in the theory of relativity that allows for time travel in certain situations. In the early 20th century, scientist Kurt Gödel demonstrated the existence of solutions to the field equations of the general theory of relativity that describe space so highly curved that they include closed time like curves. In such cases, individual timelines twist and loop themselves. This solution paves a path from the present to both the past and the future, challenging conventional ideas about time. While we're on the subject, let's discuss a few notable endeavors by prominent scientists in the realm of time travel. Theoretical physicist Miguel Alcubierre proposed a speculative scenario involving a spacecraft capable of contracting space in front of it and expanding space behind it. Utilizing this shortcut could lead to effective faster-than-light travel, possibly even enabling time travel. Other theoretical physicists have also explored similar shortcuts. For instance, scientists like Kip Thorne and Paul Davies have considered the potential use of wormholes to navigate space-time, offering a means of achieving instantaneous spatial travel. The idea of wormholes has been a popular topic, particularly in science fiction movies, as these theoretical passages link two distinct points in space-time. The threat is so twisted that these 2 points are virtually similar behind the space-time events between However, the creation of such a wormhole would demand inconceivable amounts of energy. Scientists are exploring the possibility of generating miniature wormhole conditions by accelerating electrons to near the speed of light and colliding them at facilities like the CERN particle accelerator. Nevertheless, scientists believe that such a wormhole would promptly collapse and transform into a black hole unless a method to keep it open, possibly involving negative energy, could be devised. Regrettably, while theoretically possible, this concept remains far from practical. Delving further into the causality of events, it becomes evident that time travel faces significant challenges and logical hurdles. The prospect of traveling backward in time is generally considered far less likely than traveling forward. This is due to concerns about temporal paradoxes arising from the breach of causality, often manifesting as causal loops. In our context, a causal loop refers to a sequence of events that cycles back in time, encompassing an event as one of its own causes. Consider this scenario. A woman purchases a book on time travel from a bookstore, then uses a time machine to transport herself back to a distant year. There, she presents the book to someone and impresses him with its content. He subsequently rewrites the book, ascribing it to himself. People enjoy the book, and over generations, it becomes widely published. To recap, the bookstore received the book from a publisher, the woman obtained it from the bookstore, and the publisher got it from the man. But who is the true author of the book? Where does the initial information in this loop originate? While each event in the chain has a valid cause, the chain itself lacks a clear entry point for the information. The complete loop remains inscrutable, even though each component within it is puzzling. It's one thing to inquire about the origin of a single event, but it's an entirely different matter to question the source of an entire chain of events. When trying to comprehend how an event came to be, such as the circumstances leading to your birth, you might initially consider prior events, details about your parents, their meeting, facts about your grandparents, and even general information about humanity. However, as you trace this chain of causes and effects backward, you'll soon find yourself contemplating the evolution of our place in the universe. And you may continue to backtrack indefinitely. Ultimately, there is no definitive answer to the question of where the entire chain of events originates. Now, consider another perspective, which many physicists take very seriously: the notion that causal chains can manifest without any discernible origin. Quantum physics and Big Bang cosmology entertain the idea that the laws of physics permit events to occur without pre-existing conditions. In standard Big Bang cosmology, the Big Bang is not just the first event in time. It marks the inception of time, as articulated by Stephen Hawking. The question of what transpired before the Big Bang becomes meaningless, because there is no answer. It's akin to asking what lies north of the North Pole, where there's simply no satisfactory response. There exists a point at which you can no longer invoke past events, entering the realm of causal loops, where events become their own causes. The emergence of information seemingly out of nothing indeed defies our intuitions. While individual events may have plausible explanations, there's often no way to account for the entire chain of events. It's conceivable that causality operates in such a cryptic manner the universe guards its raw information by simply not providing further explanations. This could make it fundamentally impossible for us to witness the origins firsthand, experience the ability to leap into different timelines, or alter past events in pursuit of a better future. This might represent our current best understanding of how time operates, and more significantly, how the universe operates. Space and time are intimately intertwined and dictated by the laws of physics in our universe. They serve as an expression of their interrelation and how they shape our reality.